Hi, we're going to look at one more application of derivatives here. And this one has a lot of very technical details and calculations. And so rather than get heavy into the calculations, I really want you to focus on understanding the main idea. And for Newton's method, the main idea is that we are going to be using tangent lines to approximate something else about the curve. And specifically, what we're going to approximate with Newton's method is x-intercepts of a function. And so there are a lot of different methods that you might actually use to approximate x-intercepts. So you might use calculator, you might use other graphing technology, and that's all perfectly fine. But what we're trying to focus on here is what exactly the calculator or graphing utility might be doing in the background. And so it's running some sort of algorithm, probably a more sophisticated algorithm than Newton's method, but the idea is that the key ideas underlying Newton's method would be similar to the key ideas underlying other possible algorithms. All right, so we're going to just start here with an example function I'm going to write down here. And so if I wanted to think about x-intercepts of that function, that would be when y is equal to 0. So I might put in 0 for y and then try to solve for x. The problem here is that you can't algebraically solve for x. I've got a quadratic term and then I've got this exponential term, and so there isn't algebra that actually allows you to isolate x and get x equals a number. And so figuring out what that x is equal to requires something else. All right, so I'm going to draw a graph here in a second. I'm going to do this by hand first. I'm just going to plot a few values of x. I'm just going to pick some very straightforward values of x to plug in and think about the y values here. All right, so when I plug in x equals 1, I'll get e to the 1 minus 1. E is about 2.7, so when I subtract 1 from that, I'll get about 1.7. When I put in 0, I'll get e to the 0 minus 0, so e to the 0 is 1. And when I put in x equals negative 1, I'll get e to the negative 1 minus 1. And e to the negative 1 is 1 over e. And so just ballpark approximation, e is roughly 3, a little bit less than 3. So this is close to 1/3 minus 1, or approximately negative 2/3. You can get a better approximation from your calculator. But remembering back when we talked about intermediate value theorem, I know that this function is continuous because it's made up of a sum of two functions that I know are continuous, exponential function and polynomial function. When I think about these points at 1 comma e to the 1 minus 1, and at 0, 1, and at negative 1, at approximately negative 2/3, I know that that function has to pass through the x-axis somewhere in between there. So I know that there has to be a 0. That's intermediate value theorem, tells us that this continuous function has to pass through y equals 0 somewhere between x equals 0 and x equals negative 1. So I have an x-intercept or a 0 of the function somewhere in between there. And just from this graph, I could just look at this and estimate maybe that that's about negative 0.6, just from this hand-drawn sketch that I did. But what we're going to look at here is using Newton's method to get a better approximation for that. All right, so the idea is that you start with some kind of initial guess, and maybe that guess is x equals 0 or x equals negative 1 or x equals something in between them, negative 0.6. But you start with some initial guess, and we label that x naught. I'm just going to use 0 here just for simplification of calculation here. All right, so I used x equals 0, which is close, but not maybe as close as I could be if I wanted to do something else. All right, and then the idea is that we're going to create a tangent line at that x naught value. Right, so the x naught point is 0, and the y naught point would be f of x naught. So in this case, we would have the point 0, 1, and then we need a slope, and that'll be given by the derivative. And so I'm going to calculate the slope at x equals 0. So I get the tangent line at that point, at the point 0, 1, with slope 1. So I'll have y minus 1 equals m1 times x minus 0, or y equals x plus 1. And so I'm just going to sketch that tangent line here on the graph. All right, and so the idea is that at that initial guess, I used x naught equals 0. I got a tangent line at that point. And then if I look at the x-intercept of that line, that's easy to find. I put in y equals 0 to that line, and I get x equals -1, and then I use that for my second guess. So we started with x naught equals 0, and then I get the x-intercept of that line, and that in this case was x equals -1, and that's going to be my next guess. And you just keep reiterating the process. So in general, you're going to find an x value. So here I'm going to say we're going to start with some value xn. And the next guess would come from writing the equation of the tangent line at that point, xn comma f of xn with slope f prime of xn. And then you would want to find the x-intercept of that line, so you'd put in y equals 0 to find the next x value. So if I put in y equals 0 and then solve for x, here's what I get. And then this becomes your next guess for x. So we would label this x sub n plus 1. So if you look in your textbook, there is a box with a formula in it that says this is how you use Newton's method to get new x values. And so you just keep reiterating the process. This is not something you would do by hand. This is something that's great for a computer to do because you can put this in a spreadsheet or program and just give it the initial values, and then it will spit out a whole bunch of them. So instead of actually doing some calculations by hand, you can probably find some videos on YouTube about that. We're going to let Desmos do some calculations for us here. Okay, so here you can see I have got a Desmos app, and I will put the link in our course for this Desmos app that I made here, and you can type in different functions. I've got the function typed in here that we actually started with, and then I told Desmos to calculate its derivative, and then you can use this slider to slide for an initial guess. We chose x equals 0 for our initial guess. And then I have this set up that it will do several iterations of Newton's method. I'm going to zoom in a little bit here so that we can see what's happening near that point a little bit better. Okay, so when I click this dot, it's going to show me the first iteration of what I calculated by hand when I was writing stuff out. So there's the tangent line at x equals 0, and then looking at that tangent line, the x-intercept of that line is at x equals -1. So that's going to be the next iteration. So I click that. There's an orange point there. And then it calculates a new tangent line at that point. And then our next guess would be at the x-intercept of that line. Remember, x-intercepts of lines are easy to find. Just pretty straightforward to calculate. And so if you scroll down here, this is set up to do 5 iterations. You could certainly make it do more if you want. Third iteration is green. Fourth iteration is blue, almost right on top of the green one. If we zoom in, we'll see that they're not exactly at the same place there. And then the fifth iteration here on this app is purple. I just set it up to be that way. And then I also have this app to set up to display down here at the bottom the fifth iteration estimate for x-intercept. So -0.70. And for this one, actually after 5 iterations, that's pretty close to the x-intercept of that curve. I have to zoom in pretty far to see that that x-intercept on that purple one, that last one that I calculated, is any different from the equation of the curve. It's hard to even see it as different from the equation of the curve. All right, so this is one where really even after a couple of iterations I had a pretty good approximation. And again, I don't really want you to do a bunch of calculations with this. I want you to understand the process. So I'm going to clear off all these lines, just clicking these little buttons out to the side here to clear them off. And we're going to look at another function and just talk about some issues where sometimes this might have a little bit of difficulty. So I'm going to type a different function and then we'll look at that. Okay, so this function that I've typed in here, you can see here this graph, there's a few x-intercepts here. Looks like we have a couple of different x-intercepts here. And so we're just going to look at this one. This one has a little bit more complicated behavior than the last one we looked at. And so we want to just kind of look at this and talk about when this method might work well and when it might not. So you can see from the graph here, there's a couple of x-intercepts, one between 3 and 4, and then another over here between 6 and 7, it looks like. So if I want to start with this one that's between 3 and 4, I could guess maybe x equals 3. I'm going to actually start a little farther away. Let's start at x equals 2 just so we can see what's happening here. And then I'm going to do these iterations, these tangent lines again. So there's the first one. And then you can see the x-intercept of that red line is already very close to the actual x-intercept of the function that's there between 3 and 4. But let's go ahead and do these other ones. Orange, and then green, and then the blue one almost right on top of the green one, and then the purple one pretty much right on top of the blue one. And we can scroll down here and see that 3.36996672,372 is what we get out of the fifth iteration for the approximation on the x-intercept. All right, so I want to show one thing that could happen if we're not careful with this, and that where you can run into trouble sometimes with Newton's method. So with any approximation technique, that would be important to think about. So if I happen to choose my initial point, let's say right here at x equals 5, and then I do some iterations, you can see that what's happened when I choose my initial point x equals 5, these other iterations are way over here. Part of that has to do with the fact that when I chose that x equals 5, it's got nearly a horizontal tangent at that point. And so the tangent line at that point isn't really following the part of the curve that I'm interested in approximating, but you can see these were going farther and farther away from the x-intercept that I was trying to approximate. So if I choose an starting point that's closer, we get much better approximations there, but you want to choose a point that's on a part of the curve where the tangent lines are all pretty consistent. But when I chose that at x equals 5, they were all headed off in other directions. So that's one possible situation to think about. The other possible situation to think about when you might have trouble is if you think about the actual calculations, this denominator is a slope. So if you ever get to a place where the slope of the tangent line at any point is actually equal to 0, then this calculation will fail. You can't actually divide by 0. All right, so that's why really a piece of technology like your graphing calculator or maybe Desmos, when it's finding x-intercepts, probably uses a more sophisticated algorithm than this actual one, because there are some easy places where this can fail. But the key idea here again is just understanding how tangent lines are used to approximate curves. All right, so in the homework, I'm not asking you to do some calculations. Some instructors might ask students to do that. I'm really just asking you to be able to understand and answer questions about the main idea of what's happening with Newton's method.